Hello students, we will continue our discussion on compactness in a topological space. Compactness in topological space. First we consider the open interval 0 to 1. This interval is not compact. Why? We can say it in many ways. First, it is bounded but it is not closed. So a set which is closed and bounded is said to be compact. Here it is bounded but not closed. Second method, first closed and bounded. Closed and bounded implies compactness in real life. Second method, if we take a sequence in it and we can abstract a subsequence which converges in the set 0, 1, then we say set is compact. Now suppose we take a sequence xn here, and from this sequence we abstract a sequence 1 over 2n, and this sequence converges to 0 and 0 does not belong to open interval, so it is not compact. Third method, if we want to see its compactness, suppose C is the cover of 0 1 in open interval 0 to 1, and we denote it by AI BI such that AI less than BI and AI BI belongs to RI 1 2 and so on. Suppose it is the cover of this, that is, or you can denote it, or see, you can denote it G lambda, lambda belong to gamma, where G lambda is of the type A lambda B. Now it is covered, so 0 to 1 can be written as union or AI BI. We assume, suppose it is a finite subcover. From this cover, if you are able to draw a subcover, then we say it is compact, otherwise it's not compact. Suppose we able to draw a finite subcover. 0 to 1 is written as 0 to in, this finite subcover AI. Suppose it is finite subcover. Let epsilon be minimum of A1, A2, AN. Now we observe that 0 to 1 is equal to union I1 to N, AI BI is contained in epsilon 1, but 0 epsilon intersection epsilon 1 is empty. So from here we observe that the element which is between these two elements is not covered by this cover, so it is not compact. So this cover has not a finite subcover. Fourth method, we can also take, suppose the cover of 0 to 1 is written as union or n belong to n, 0 1 minus 1 plus n is the cover of this. Suppose it has a finite subcover. Now this subcover is 0 to 1 is union n 1 to m, 0 1 minus 1 plus n. Now suppose this is a cover, suppose it is finite subcover. Now let n star maximum of 1, 2, 3 up to m. This n star does not belongs to union I1 to m, n1 to n1 to m, 1 minus में 1 plus में n star. Hence again we say that 0, 1 is not compact. Now in case of metric space and in case of topology, in metric space we consider two methods. First, if every sequence has a convergent sequence, every open cover is a finite subcover. These two methods are useful in metric space, but in topological space, if every open cover has a finite subcover, is most appropriate method to see the compactness in a topological space. Okay, now we come to arbitrary union of compact set need not be compact. Need not be arbitrary union of compact set need not be compact. Now we consider the usual topology. In usual topology, a closed and bounded when X is R. In usual topology, a closed and bounded set is compact. Now we consider the set. Now we consider set 0, 1 minus में 1 over n. This is closed and bounded and this is compact. If we add it over n, then we will get here 0 to 1. This is closed and bounded compact, but their arbitrary unions comes equal to 0 to 1 over interval, so it is not compact. Now we take another example. Let X is equal to infinite set and T be a topology, P exclusion topology. Phi A is a subset of X such that P does not belongs to A. Here this topology is also compact, because in this case the cover of this is only the whole set, a singleton set. Okay, so this is P exclusion topology. P exclusion topology is compact because its cover is only singleton set X and is finite. It has a non-finite subcover, that single set. Now we come to every compact subset of a orthogonal space or T2 space is closed. Proof. Every compact subset of a Hausdorff space or T2 space is closed. Let XTB a T2 space. Every compact subset of a Hausdorff space. Let XTB a T2 space. Let B be a compact subset of XT. Now we saw B is closed. To show B is closed, we need to show B is closed, we need to show X minus B is open. Now Now let x belongs to, we take an element x belongs to x minus b. We will show here that each neighborhood of this is contained in the x minus b. Then we show it is open and its complement, then it is closed. Let x belong to this. This implies x belong to x and x does not belongs to b. Now we take an element y belongs to b which is not equal to x, and this is contained in x. From here we observe that we have obtained two elements x and y which are distinct and which belongs to x, and x is T2 space. X is T2 space. So for two distinct elements we can get two joint open set such that let gx and hy be two disjoint open sets such that x belongs to gx and y belongs to hy, and gx intersection hy is empty. Now from here we observe that y belong to b, here y belong to hy. From here y belong to b and this y is covered by open set hy, so this is the open cover of b. So b can be written as b union y belongs to b hy, but b is compact, so it is a finite subcover. Since b is compact, so we can draw a finite subcover, and that is further can be written b is contained in union I union hy I1 to n. Now this is denoted by h. Further, corresponding to these y's y1 y2 n, we can get corresponding element x1 x2 xn, so we can write g is equal to intersection I1 to n g x I, and we observe that h intersection g is empty. B contained in h and h intersection g is empty. This implies h complement is contained in b complement and g is contained in h complement. From these we conclude g is contained in h complement and this contained in b complement. Now g is contained in h complement, g is contained in b complement, and this implies x belong to g is contained in b complement. This implies x belong to g contained in x minus b. Hence x minus b is neighborhood of each of its points. Hence x minus b is open. Hence this implies b is closed. B is closed. Thus we conclude that every compact subset of Hausdorff series is closed. A compact T2 space is T3 space. In fact, it is regular. It is regular. Now you know what is T2 space. You know what is T3 space. You know what is regular space. Regular space. A space is said to be T2 space if for every pair of two distinct points we have two disjoint open set like this. Two distinct points we have two disjoint open set. It is G and it is H. G intersection H is empty. For two distinct points X and Y, we have two disjoint open set. Now a space is said to be regular if for any closed set B and X does not belong to B, there exists two disjoint open sets such that X belongs to G and B is contained in H, or G intersection H is empty. This is said to be regular space. A space, and this can be shown like this. This is point X belong to G, and this is the H, and B is like this by strip closed. This is B, this is H, this is G. Now a space is said to be T3 if it is T1 and regular. If it is T1 and regular. A space is said to be T1 if two distinct points X and Y, we have two open set, they may be disjoint or they may not be disjoint, such that one point belong to this, and they may be like this, another point belong to this. This is G and this is H, and they may be like this, X and Y. This is T1. Now come to the proof. We have to prove it is T3 space. To show T3 space, we need to show it is regular and T1. It is regular and T1. But a T2 space is always T1, therefore we need to show that it is regular space. Now we show it is regular space. Proof. Let B be a closed subset of a T2 space and X does not belong to B. Now for each Y belong to B, where B is contained in X, we have two distinct points X and Y which belong to X. Here X is a T2 space. Now a space is said to T2 space if for every pair of two distinct points we have two disjoint open set. Now we say Gx and Hy are the two disjoint open sets such that X belong to Gx and Y belong to Hy, and Gx intersection Hy is empty. Now this Hy is the open cover of B. Now Hy is the open cover of B. Now B is contained in union Y belong to B, H of Y. Now B is closed subspace of a T2 space, so it is compact, so it has a finite subcover. So we can abstract a finite subcover from this cover of B, and that is B is contained in union I1 to N HYI. Now for distinct point Y1, Y2, Yn, we have distinct point x1, x2, xn. So we can write x belong to intersection I1 to N GXI. Now we denote union I1 to N HY by H, and we denote intersection I1 to N GXI by G. From here we observe that B is contained in H, X belongs to G, and G intersection H is empty. To show G intersection H is empty, suppose it is not empty, that is, it is non-empty. Now it is non-empty, we take a point P belong to G intersection H. Now point, this implies P belong to G and P belong to H. Now P belong to G mean this P is belong to G, I for all I, and P belong to H mean P belong to some HY, I for all I, P belong to GI, or you can say P belong to GXI. Now from here P belong to GXI and P belong to HYI. This implies P belong to GX intersection HY, but we already said GXI intersection HY is empty, hence G intersection H is empty. Hence we conclude that for a closed set B and a point which X does not belong to B, we find two disjoint open set H and G such that B is contained in H and X belongs to G. Hence we say that a compact T2 space is regular, but a T2 space is already T1, hence it is T3 space, because a space is said to be T3 if it is T1 and regular. A T2 space is T1 and we proved it is regular, hence it is T3 space. Now we come to next term. A compact T2 space is normal. In fact, it is T4 space. Proof. Before going to start proof, what is normal space? A space is said to be normal a pair of two disjoint closed set. We have two disjoint open set such that if C1 and C2 are two disjoint closed set, C1 intersection C2 is empty, we have two disjoint open set H1, you can say H2, H1 or intersection H2 is empty such that C1 is contained in H1 and C2 is contained in H2. We can show like this. This strip denotes the closed set C1 and this is H1 and this is H2 and this strips present C2. For two disjoint closed set, we have two disjoint open set H1 and H2. That space is said to be normal. A space is normal and T1 is said to be T4 space. T4 means a space which is T1 and normal. A T2 space is always T1 space. So to prove it, we only need to show it is normal. Now start the proof. Let A and B are two disjoint closed subset of compact T2 space. A and B are two disjoint closed subset of a compact space. Now we already know we already know a compact T2 space is regular. A compact T2 space is regular. Therefore, X does not. Therefore, it is regular space for a closed set B. X does not belong to B, and for each X belong to A. We have two disjoint open set Gx and Hx such that X belong to Gx and B is contained in Hx, and Gx intersection Hx are empty. Now we have find an open set for closed set B. Now it needs to find an open set which contain A. For this we have to form a relative topology. The relative topology is formed as T of A. With the help of this closed set and this open set, we form the relative topology A intersection Gx such that X belongs to A and Gx belongs to T. This is the relative topology. Now this open set is the cover of A. Now A is contained in union A intersection Gx. X belong to A. A is closed already. A closed subset of a compact set is compact, so it has a finite subcover. So this can be written as, we can abstract a finite subcover from this open cover. This can be written as A is contained in union I1 to N A intersection Gxi, or we can write it A is contained in A intersection union I1 to N Gxi. This implies A is contained in union I1 to N Gxi, and we denote it by G. Now we have this an open set G which contains A, and B is also closed subset of a compact set T2, so B is also compact, so B can be written as intersection I1 corresponding to these element x1, x2, xn. We can write as B is contained, in fact B is contained in intersection I1 to N Hxi, and we denote it H. Now we have obtained two open sets G and H such that A is contained in G and B is contained in H, and G and H are both disjoint. Now to show they are disjoint, suppose P belong to G intersection H. This implies P belong to G. This implies P belong to G and P belong to H. P belong to G mean this implies P belong to Gxi for some xi, and P belong to H mean P belongs to H x for all I, for all xi. This implies P belong to Gxi intersection Hxi, but Gxi and Hxi are disjoint, so we say this is P belongs to phi. This implies G intersection H is empty. Hence we have obtained two disjoint open set for these two closed sets, as A is contained in H, B is contained in H. Therefore from here we conclude that Xt is normal. Xt is normal. Suppose for two disjoint closed set we have trace out two disjoint open set, but we are already given T2, a 2T is always T1, so space is T1 and normal is known as T4 space. Now we come to an example. Intersection of two compact set need not be compact. Let X be an infinite set and T be topology, exclusion topology, in fact, such that A is contained in X and P and Q does not belongs to A. This is a topology. Now we form two subset Y such that Y is equal to X minus P, and we form its relative topology Ty such that A intersection Y such that A belongs to T. Now this topology become Q exclusion topology. Now we another take set Z, which is written as X minus Q. Now we form its relative topology Tz, and this is written as A intersection Z, where A belongs to T. This topology belongs to P exclusion topology. We already proved an exclusion topology is a compact topology, compact space. Exclusion Ty, this is a compact, now this is compact. Now we find Y intersection Z is equal to X minus P Q. Now if we form the relative topology Y intersection Z, this is A intersection Y intersection Z, where A belongs to T. Now this topology T Y intersection, you can check it is a discrete topology on Y intersection Z on infinite set, and the discrete topology is not compact. Hence we observe that intersection of two compact set need not be compact, because P exclusion, Q exclusion, these both are compact, and this T Y intersection Z, this is not compact, because from here, from this topology, we after calculation we come to discrete topology in Y intersection Z, and discrete topology is not compact, you already know. Hence intersection of two compact set will not be compact.